And the reason for this is non-thermal dust emission. When you consider dust grains, every photon that is absorbed heats the dust grain, and the smaller these grains become, the more the heat capacity of the dust grain is comparable to the energy of the incoming photons, so that a single photon absorption very rapidly heats up the grain considerably. So when you model this, you see that for very large grains, absorption events marginally heat the grain, and then it cools up. And the smaller the grains become, you have here an absorption, and then it cools, and then the next absorption, and so on. The smaller the grains becomes, the more difficult it becomes to actually define a mean dust temperature. Here in this case, this is very simple. This is the mean temperature. Here it's also possible, though that would be the mean temperature. But when we look at very small particles, the concept of mean dust temperature becomes more meaningless, because only for a relatively short period of time the grain has a high temperature and then it cools down, and it takes a long time before the next hit by a photon heats it up again. So the concept of a mean dust temperature is here more meaningless, because of course if this is the mean temperature, basically most of the time the grain is much cooler, and if it's warm, it's actually most of the time much hotter. So we are actually looking at a time series of random heating events, and we leave the assumption of a steady state. So this can be described in terms of a probability distribution for how many particles you expect to find at a certain dust temperature. This is shown here in this figure. For very large grains, what you have is basically a delta function at a single temperature. And the smaller the grains become, so this is here the radius, the wider this distribution becomes. So for example, at 50 angstrom, this is here the distribution, the probability distribution in log space. And you see that the smaller it becomes, the wider this distribution is. So you have a less defined mean temperature, and the average temperature is higher than the LTE case. So smaller particles on average are warmer than larger particles. And this explains here this mid-infrared excess that takes place between a few micrometer and maybe 20-30 micrometer. And on top of that, we also find discrete, more or less discrete features that are created by vibrational bands in these very small grains. So basically we are moving from a solid particle closer to a very large molecule, where we have bending and stretching modes that can be also activated and radiate at very dedicated frequency or in a smaller band. And these are the peaks here. These are the PAH features for polycyclic aromatic hydrocarbons. So very large molecules that are built up from benzene ring constituents. However, this excess in the mid-infrared allows us to determine the lower end of the dust size distribution, so how many small particles make up the overall dust population.